Welcome back. Justin Miller, Outside College Physics here. We are going to be looking at some more diffraction, but we're going to look at it with a new case here. Not single slit, not double slit, but a whole bunch of finely spaced slits all together, which ultimately comprise what is known as a diffraction grating. Now, it could be grooves or slits. There's reflective diffraction gratings and transmissive diffraction gratings. A CD acts like a reflective diffraction grating. The little grooves on the CD itself are so finely spaced together that when the light strikes it and bounces off, it undergoes a large amount of diffraction and interference takes place, and ultimately that's why you see all these colors on the CD because of diffraction and interference taking place. So while the CD's of interest, we want to look at a more standardized diffraction grating here. So I got a little system set up here where the diffraction grating is actually transparent. You can see through it. And then I got a laser set up here, and I got this little thing to capture the light on. Hopefully get a little bit better resolution out of it. But ultimately, let's take another one out right here. I can take one of these diffraction gratings. Maybe you see some colors, maybe you don't. Moving it around. Anyways, I can take it and I can shine some laser light, monochromatic light through it and see what happens. So I'm going to do just that. And you should notice there that there is that central maxima right there. But then I get these very large spacings between the successive maxima. And ultimately, the system is dominated by destructive interference. We get these really nice discrete locations of constructive interference, these bright spots here. So diffraction gratings ultimately produce a larger extent, angular and spatial extent of the separation between the successive maxima. And because everything's dominated ultimately by destructive interference, all we need is one nice little expression that involves, hey, where did the maxima occur out angularly, or what is the angular correspondence to where the maxima occur. So what I want to look at, before we get into mathematics here, is just a system where I've got two different colors of light here. I got a laser that produces two colors. It's got a red and a green. And what I want to do is activate them both simultaneously. Hopefully that will work for me. And that may or may not be the case. Get that a little tighter on there. Ooh, come on, red. It doesn't really want to cooperate that much. This tape's no good. All right, so ultimately, what you should be able to see is without them going through the diffraction grating, we've got the green light and we've got the red light. They're kind of lined up vertically, and then I'm going to put them through the diffraction grating. And what do you notice that happens? I can keep them both on at the same time. It's harder than it seems, huh? All right, there we go. Well, here's the central maximas right there, and they're flanked by the successive first order maxima, second order maxima, and so on and so on. But one thing of great interest here is not just a large separation between the successive maxima regarding a particular color, but also that, hey, the distance from here to here is not the same as the distance for the green, right? From the central maxima to the first order maxima. It's fairly apparent that they undergo different amounts of angular separation. So what this ends up being very important for is looking at light sources that have composite wavelengths of light in them, more than one wavelength. And what you can start doing is getting great separations angularly of those different wavelengths of light. You can start utilizing that to correspond to what type of material it is. All sorts of things go into the analysis of light in general. It's something that we'll be looking at here a little bit later on when we start looking at the hydrogen atom and atomic spectra and all that good stuff. But for now, we just want to focus our attention on this diffraction gratings and talk about them a little bit and kind of move on from there. So let me move this stuff out of the way really quick so I do not knock it over, as I'm quite prone to do. Scoop this right, and I'll even take this off. Ooh. All right, so diffraction gratings. It's basically a series of finely separated slits, lines, or grooves. Slits. Grooves, good, okay. Gratings. Produce. Large amount of destructive interference. Regarding light that is directed upon them. This ultimately leaves, I won't say ultimately, this leaves very discrete locations of constructive interference. Discrete locations regarding constructive interference. With considerably large angular separations between successive maxima. All right, whew, that was a little writing exercise there. Diffraction gratings. Categorize. Diffraction gratings are rated by what is known as the grating constant. And we just use R for representing the grating constant. What is the grating constant? Well, the grating constant tells how many lines, grooves, or slits there are per unit distance. And why is that important? Well, ultimately it correlates with the slit separation, or the separation in between the successive slits, lines, or grooves. So this particular diffraction grating, I'm holding my hand, says 600 lines per millimeter. That is, there are 600 separations in 1 millimeter across this material here. I can't see the separations, they're there though. So it's like there's 600 thin slits, in a sense, that are within 1 millimeter of this. That's a whole bunch, right? So we just think about double slit diffraction. This ultimately produces an amplification of that because there's so many successive double slits and they're really finely separated. What we ultimately get is an angular correspondence for diffraction gratings. Diffraction gratings. We have that the maxima occur according to the expression. Oh, it turns out to be a really familiar expression. D times the sine of theta is equal to n lambda. Basically the same thing that we had with double slit diffraction, right? It is. This is how the maxima occurred. However, we don't say plus and minus anymore. We just say that n is equal to 0, 1, 2, 3, dot. And talk about the first order, second order, third order. Everything's symmetric about the central maxima at n equals 0 along the principal axis. And that's basically that. What we need to appreciate is this D right here. D is the slit separation. And, well, how do we get D? Again, generally, we're given some grading constant that tells how many lines there are per unit distance. D ends up being the inverse of R. D is equal to 1 divided by R. There's 500 lines per millimeter, then 1 millimeter divided by 500 tells you what the slit separation is in millimeters. So that's just something to take into account because we need to know what the slit separation is. Let me just use this. There is no expression for destructive interference because destructive interference occurs everywhere else except where the maxima are produced. And that is substantial. It's not such a tightly compact interference pattern anymore. It's very discrete regarding the location of the maxima and heavily dominated by destructive interference, as we saw there. All right, so really it's just using the same expressions, type of expressions that we've been using with diffraction interference. And again, the nice thing about the diffraction gratings is we can start to have large separations between different wavelengths, so we don't require monochromatic light anymore. You start shining white light through diffraction grating, you start getting rainbows because there is this large angular separation regarding different wavelengths of light. Furthermore, because we have large angular separations, you cannot start utilizing small angle approximations, which I just suggested not to do in the first place with single and double slit diffraction, but some people still like to do it. You can't do it with diffraction gratings because this angle here tends to be a fairly large angle, depending on the grading constant, but it exceeds the small angle approximation limitations and thus should not be utilized. All right, so how about we just look at a little problem? We can kind of see how this all is laid out and draw a nice little picture. And I'll kind of do that for diffraction. And we'll move on. All right? Sounds good. Be right back. Do a problem. All right, let's get that problem going. So we've got ourselves a diffraction grating that has a grading constant of 600 lines per millimeter. We're going to put a screen 1.5 meters away from that diffraction grating. And what do we observe? We observe some maxima. We've got a central maxima, which is just the composite light, and then we've got some other maxima. What we want to do is utilize some measurements that we can make regarding separations between maxima and figure out what wavelengths of light are actually in that composite source. So here's the actual problem. All right, so we've got ourselves that on some screen 1.5 meters away from the diffraction grating, we've got a central maxima, and then we've got these first order maxima. One of them has some red light, and one of them some blue light, and those two maxima are a distance of 0.635 meters from the central maxima on the screen and 0.453 meters from the central maxima on the screen. And the question becomes, well, what is then the wavelengths of light that are in that composite source? So let's draw a little depiction of this out, shall we? So we can go ahead and take our grating here. We can have some incoming composite light. Incoming arrow hits this. Well, we've also got this principal axis from which everything is measured. And then we go ahead and we say, well, we've got a screen. A little closer here. It kind of goes like this. Ooh. Straight screen that is a distance of L is equal to 1.5 meters away. And this is what we've got going on for us. Along the principal axis, M is equal to 0, theta is equal to 0, and we get the red light and the blue light both join together there and ultimately look just like the light that was incoming before, which got this composite light there. All right, so we get this central maxima, M equals 0, central max, all wavelengths. So that's great. That's just going to be a good place that measure things from. And then we see this. We see a distance of 0.453 meters relative to the principal axis along the screen here. We've got ourselves this nice first order maxima. M equals 1 blue. First order max. And we've also got this distance here. We're going to call Y1 blue, which is going to be equal to, well, 0.453 meters. All right. So we got that, but we also see some red too. And the red is 0.635 meters relative to the principal axis. So let's just say that that's about like here. So we've got an M equals 1 red. It's the first order max. And it too has its distance away from the central maxima. This is Y1 red, is equal to 0.635 meters. So this is what we've got going on. We want to utilize this information here in order to determine what the wavelengths of light are. So some things that we will likely need is some angles. We've got this angle here, it's theta 1 red, the angle at which the first order maxima for the red light exists at. And then we've also got this angle here, theta 1 blue, the angle at which the first order maxima regarding the blue light exists at. So we're going to use this information then, along with some expressions to determine what the wavelengths of light are. We've got this, right? D times the sine of theta is equal to m lambda in general. And we've also got that y is equal to L times the tangent of theta in general. So we're only looking at the first order maxima at this point. We'll just go ahead and go on with that, shall we? We shall. All right, so what do we need? We need to know what is the angle so that we can figure out the wavelength, and we need to know what is the grating constant. We're going to get the angle through this expression here because we know the distance of separation on the screen. and we know how far away the screen is, so that's easy. Once we get the angle, we can evaluate what lambda is based upon the first order maxima, and d being equal to 1 divided by r. So let's just get something that we're going to need. Number one, we've got that d is equal to 1 divided by the grading constant. Be a little bit careful, it's not just 1 divided by 600, because that's 600 lines per millimeter. The inverse of that is 1 millimeter per 600 lines. So this is equal to 1 times 10 to the negative 3 meters, that's 1 millimeter, divided by 600. You could put 600 lines, but really we're just looking at spatial separation. And that comes out to be 1.667 times 10 to the negative 6 meters. 1.67 microns, 1/2 of a micron. Really, really small slit separation. Very fine separation, I should say. All right, so we can then start looking at figuring out the angles. What is theta 1 red? What is theta 1 blue? So let's do that. We'll do it in the colors, shall we? So utilizing this expression, we've got that theta 1 red is going to be equal to the arctangent of y1 red divided by, lowercase y1 red divided by L, which is then arctangent of 0.635 meters divided by 1.5 meters, which gives us the angle of arctangent 635 divided by 1.5 gives us 22.945. 22.945 degrees angular separation between the first order max and the 0th order max regarding the red light relative to the principal axis. So we've got that for the red light. Let's get it for the blue too. This is the same sort of expression here. We've got theta 1 blue is the arctangent of y1 blue divided by L, which is the arctangent of 0.453 meters divided by 1.5 meters, and that's going to give us tangent 453 divided by 1.5 gives us 16.804. Sounds fantastic. 16.804 degrees. So notice something, the shorter wavelength doesn't undergo as much angular deviation regarding the first order maxima comparative to the longer wavelength. Shorter wavelengths have a more compact pattern than longer wavelengths. Anyway, what we want to do, we want to use this to go ahead and figure out what is the wavelengths. What are the wavelengths? So now we're looking over with this expression here, and ultimately m is equal to 1. We can just write ourselves out that lambda is going to be equal to d times the sine of theta divided by m. M equals 1 for us. So with this, we've got that lambda sub red is going to be d times the sine of theta 1 red divided by 1. We know that d is 1.67, negative 6 times the sine of 22.945. So we do 1.667 times 10 to the negative 6 meters times the sine of 22.945 degrees, which gives us sine of 22.945. 6.498, 6.499, 6.50 times 10 to the negative 7 meters. Does that look like red light? The answer is yeah, that's 650 nanometers. So, red light in there, that's its wavelength, 650 nanometers. Fantastic. What about the blue light? What is its true wavelength? do the same thing. We've got lambda sub blue is equal to d times the sine of theta 1 blue divided by 1 is the 1.667 times 10 to the negative 6 meters times the sine of 16.804 degrees divided by 1. We need that 1 in there. Let's try to do this quick. Oops. 804. Get, let's call it 482. 4.82 times 10 to the negative 7 meters, which is 482. There we go. We have figured out what wavelengths of light are in that composite source. Pretty nifty, right? So that's one of the really good uses for diffraction gratings, is to be able to see what is in this composite source of light, what wavelengths are in there. Because some things have very particular wavelengths that can then be used to identify what that substance is. And that becomes really important in spectroscopic analysis. You start looking at stars, all sorts of stuff you start doing with this. We'll talk about that more later. Let's just finish up this problem, shall we? All right, so the next question was, what is the linear separation on the screen between the second order maxima regarding the red and blue light? So we're assuming here that there is going to be some second order maxima. We don't really know where they are, so we can't put them on there yet, but we can calculate it out, right? We can get a theta 2 blue and a theta 2 red, figure out what y2 blue and y2 red are, and look at the difference between them. So let's get the datas first so that we can have an idea of where to put them on there. Then we'll put them on, and then we can look at that linear separation. Draw it out so you can see exactly what we're doing here. So, excuse me. We've got the wavelengths. They're just erased, but note that lambda sub red was equal to 650 nanometers, and the lambda sub blue was 42, oh, 482 nanometers. All right, so we got the wavelengths of light. We just want to know, first, find theta 2 red and theta 2 blue, the angles at which the second order maxima occur at for the red light and the blue light. So again, we're coming up to this right here, and we can get that in general, that theta is equal to the arc sine of m lambda over d. So we'll do it for the red, we'll do it for the blue, and then we're done. We're not done, we're done with the ends. All right, so we've got theta 2 red is going to be equal to the arc sine of 2, because m is equal to 2, times lambda. Be careful putting in lambdas because this is nanometers right here. We don't want to mix up different unitizations. I just suggest I just put everything SI again. So we've got this multiplied by 650 times 10 to the negative 9 meters. That then is divided by D, put D in terms of meters as well, 1.667 times 10 to the negative 6 meters. And what do we get out of this? Let's see here. We've got the arc sine, 2 times 650 divided by 1.667, and then negative 6, and 51.246. 51.246 degrees. That's a pretty big angle, right? No small angle approximations here. The first one was even at 22-something degrees. No small angle approximations. So let's look at the blue as well. 2 blue is the arc sine of 2 times 482 times 10 to the negative 9 meters divided by 1.667 times 10 to the negative 6 meters gives us excuse me. Let's change that to 42 and 35.330 degrees. So those are the angles at which the second order maxima occur at. If we just wanted the angular separation between the second order maxima regarding the red and blue line, let's take the difference between them. But we are specifically asked, what is the linear separation on the screen? By what distance are they separated by? So let's sort of approximate to some degree where, because it's degrees, some degree where these particular maxima occur at. So this was like 22 degrees, so we'll put like 30 something up here. This isn't going to be scaled out perfectly, but I'll say that there is n equals 2 blue, the location of the second order maxima, and this is going to be stretching things a little bit here. This won't be scaled too well. Extend the screen out, and we'll call the red way up here. M equals 2 red, such that if we measure the angles to the blue and to the red, we get 35 and 51 respectively. So this is what we're actually asked for. We are asked for this distance here. Delta Y2 red blue. What is that linear separation there? So what do we have? Well, we're going to have a Y2 red and we're going to have a Y2 blue. The difference between those two, that should be what we're looking for. And that is indeed the case. So I can go like this. Let's say Y2 red. Whoosh. Draw another one. So there's Y2 blue. So that this right here just has to be equal to the difference. We've got ourselves Y2 red minus Y2 blue. If we expand that out, we know how to know what the Y values are. We've got this is going to be equal to L times the tangent of theta 2 red minus L times the tangent of theta 2 blue. There we go. So at that, we can stick that stuff in here and go ahead and figure out what that separation distance is with relative ease. And here's the angles. Let's just do this. We'll do it right over here. So delta Y2 red blue is going to be equal to, factor out that 1.5 meters multiplied by the difference of the tangents of those angles. So we've got that tangent of the red 51.246 degrees minus the tangent of the blue 35.330 degrees. And that gives us delta Y2 red blue being equal to, hold tight, 1.5 times the tangent of 51.246. Tangent 35.330. Bracket 0.805, call it. 0.805 meters, separated by 80.5 centimeters. So pretty big. That's it. That's pretty cool, huh? So what do you notice? Well, here the separation between these two was what, like 16, 17, 18 centimeters. And then what happens? Well, we go up and look at the separation between the next two, and it's a lot greater. And for the next ones, the m equals 3, it'd be even greater, because we get greater and greater angular separations regarding the higher order numbers. So here's another question for you. How many maxima are there regarding the red light and the blue light? What does M go up to? Does M just keep on going up into infinity? We just have a bunch of little spots all the way out to infinity? Or is there some limitation? So what you got to think of is what is the limits of the locations regarding the maxima themselves. This can start getting larger and larger and larger and larger and larger, still making it to a screen, right? But 90 degrees is sort of the limitation there. You can't have maxima occur at angles larger than 90 degrees. And 90 degrees can't occur at either. So that's sort of the dividing line. So it really comes down to what M value for a particular diffraction grating and a particular wavelength of light is the maximum M value. So this can help us discern how many maxima we will see. And again, it's going to depend on the wavelength and the diffraction grating being used. So maximum is such that theta does not exceed 90 degrees. So let's look at this, right? If that's going to be the case, we have to have that M lambda divided by D does not exceed 1. Otherwise, we are exceeding the limitations of sine of theta. So, what does that ultimately tell us? It all comes down to the ratio of lambda and D, which can only be positive values. So, we have that M has to be less than D divided by a lambda. So let's look, for instance, for this red light. We've got the wavelength 650 times E negative 9 divided by, excuse me, inverse of it, so I'm getting wrong. So we get this, actually, for the red light, D divided by lambda sub red. Well, D divided by lambda sub red for our particular case is 1.667 times 10 to the negative 6 divided by 650 times 10 to the negative 9. Go ahead and compute that out, and that comes out to be 2.56. 2.56. M must be an integer and is less than 2.56. So M equals 2 is maximum order number for the red light. So that's as many order number as we see for the red light. There is no M equals 3 because it doesn't exist, can't exist for this particular diffraction grating. A lot of it's hinged upon this. So let's look at blue. M max blue, well, that's going to be equal to D divided by lambda sub blue, which is equal, must be less than that, where that is equal to 1.667 negative 6 divided by 482. Negative 3.49. 3.49. So, M max for the blue is equal to 3. So while there is only up to a second order maximum for the red, there's actually a third order maximum for the blue. And that's pretty much, I'd go ahead and start looking at how many maxima do you see. Change D, change how many maxima are possible for a given wavelength of light. And the larger D is, the more maxima there are. Smaller D is, less maxima. But greater separation annually. Anyways, these are kind of some fun things that we can do with diffraction gratings. And I'm that's incoming. Anyways, that's that. Good day.